Welcome to This Explainer. Today, we're diving into a 2026 paper by Dan Adrian German called A Term-Rewriting Semantics for Pure Quantum States. Now, I know that sounds like a mouthful, but stick with me because this paper literally rewrites how we can teach and honestly, deeply understand complex quantum physics. If you've always thought quantum mechanics was this impenetrable fortress that permanently required a PhD in linear algebra just to grasp the basics, well, this is going to completely change your perspective. We're looking at a framework here that strips away all that dense mathematical abstraction and just reveals the pure mechanics underneath.
So let's start with a kind of provocative question. Can a middle schooler actually calculate quantum states? For decades, the reflex answer has been an absolute, undeniable no, right? I mean, the traditional gateway into quantum mechanics is heavily guarded by this formidable wall of infinite-dimensional Hilbert spaces, complex probability amplitudes, and these massive dense matrices. Getting any sort of physical intuition usually means years of grinding through high-level calculus first. But what if that barrier is largely an illusion? What if the core concepts of quantum circuits and computations could be manipulated and understood using tools we all learned way before high school?
You know, traditionally, diving into quantum theory feels a bit like trying to scale a massive cliff of complex numbers and differential equations. Sure, it's rigorous, but it is incredibly opaque for a newcomer. The paper we're unpacking today makes a really bold argument. We don't actually need to scale that cliff on day one. Instead of relying on a continuous spectrum of complex amplitudes just to track a state, it turns out we can use a remarkably simple set of arithmetic rules to pull off accurate, highly meaningful quantum calculations. To really appreciate why this paradigm shift is so absolutely crucial, we gotta look at the core friction in physics education. By front-loading all this incredibly dense math, we end up obscuring the actual physical intuition of what a quantum system is doing. It's literally like forcing students to memorize the thermodynamic engineering manual before we even let them sit in the driver's seat of the car. By gating quantum mechanics behind high-level math, we're locking out brilliant minds who could otherwise completely grasp the fundamental physics if they just had the right conceptual tools in front of them. And that brings us to the hero of our story, really, a brilliant foundational solution introduced back in 2017 by Terry Rudolph, known as MISTY states. Rather than calculating constantly shifting, complex probability amplitudes using gigantic matrices, MISTY states give us an elementary term rewriting system. Basically, think of it as treating quantum states more like classical-like states that evolve through very specific, rule-based arithmetic replacements. So you apply a quantum gate, and instead of doing a bunch of matrix multiplication, you simply follow a discrete rewriting rule to update the state. It's a real game changer because it allows learners to accurately track and describe quantum circuits by focusing on the logic without getting bogged down in traditional algebra. Now, I want to be super clear about something. This isn't just some oversimplified toy model. Rudolph's MISTY states leverage Yayunje's foundational mathematical results on universal gate sets. That ensures this simplified arithmetic doesn't somehow break the actual laws of physics. Plus, the whole system leans heavily on the powerful quantum formalism developed by A.A. Kataev. Because it's built on the exact same underlying logic as the heavy mathematics, the MISTY framework remains incredibly robust and physically accurate. It's just translated into a much more accessible dialect. The sheer capability of this system is, frankly, mind-blowing. The MISTY formalism is simple, accurate, and completely universal. By using just a tiny, highly restricted set of gates and this term rewriting arithmetic, you can perform literally any quantum calculation to a good enough accuracy. And when the paper talks about doing this with only a small overhead, what that means in practical terms is you're really just adding a few extra arithmetic steps, or maybe using a couple of extra uncilia qubits to keep the computation going. You aren't sacrificing the physical truth, you're just taking an easier path to the exact same destination. Now, the ultimate goal of this paper isn't to just permanently tear down and replace the conventional quantum mathematical apparatus. The established math exists for a reason, for sure, especially when we get into advanced applications. Instead, think of MISTY states as a highly effective transition, a bridge. Once a student grasps the fundamental logic of quantum circuits, things like entanglement, superposition, interference, through these MISTY states, mapping that intuitive knowledge directly onto standard Dirac notation or state vectors becomes a nearly frictionless process. It builds that mental muscle first, making the traditional math way less intimidating when it finally does show up. But the story doesn't end with Rudolph's initial proposal back in 2017. Fast forward to July 2026, and Dan Adrian German picks up the mantle. His goal, to push this framework out of the purely theoretical realm and into highly practical, complex applications.
German actively tests the strengths of this elementary MISTY state picture by deliberately applying it to advanced multi-qubit scenarios. He basically wanted to see exactly how far term rewriting semantics could be stretched before the abstraction breaks. And what he finds is incredible. German's 2026 paper expands the semantics to evaluate if this simple arithmetic can genuinely hold its own against advanced quantum phenomena. He set out to generalize this term rewriting system to handle true quantum non-locality and multi-qubit entanglement without the whole mathematical structure collapsing in on itself. And guess what? He proves that this simplified framework can smoothly process some of the most complex benchmark problems in physics. He's effectively handing educators a rigorously tested, immensely powerful new tool. So how does he do it? German systematically proves the framework's robustness in a few distinct phases. First off, he successfully simulates entanglement swapping, which, by the way, is a highly non-trivial protocol where two qubits that have never directly interacted suddenly become entangled. Pretty wild. From there, he introduces a fascinating new mathematical object, irreducible MISTY states. He establishes these irreducible states as acting fixed points within the semantics. This means they act as stable baseline representations that don't constantly shift around during computation, which drastically cuts down on the logical overhead. Finally, he takes these irreducible states and proves the system's true power by running the famous GHZ game, a quintessential thought experiment and benchmark of quantum non-locality, entirely through this basic arithmetic. He maps out a direct, completely understandable path through some incredibly deep quantum waters.
As we wrap up this explainer, I want to leave you with this exciting thought. If we can teach middle schoolers to master complex phenomena like entanglement swapping in the GHZ game today, just using MISTY states, what kind of quantum algorithms are they going to intuitively build tomorrow? By removing the massive mathematical walls that typically block first-time learners, Dan Adrian German and Terry Rudolph are opening the floodgates for a completely new generation of intuitive physicists. It's a profound shift, proving that sometimes the greatest mysteries of the universe don't necessarily require harder math. They just need a better translation. Thanks for exploring this framework with us.